Hello, it's James from XRobots.co.uk. This is part 15 of Project Ultron, the real robot, which is mostly 3D printed. There's quite a few episodes already. Last time I got some motion out of it by putting feedback on each of the main actuators for the shoulder so that it actually moves and I could turn a knob and have the axis move. But the entire plan for this, have a look at part 1 and also part 3, was to get this working from a motion capture suit which I built early on, and I've got it stood here on Morris the mannequin. And this is made of multiple inertial measurement units like the ones I used in BB-8 that will track the limb motion. In part 3 I actually did make a small test arm that worked from one of these inertial measurement units, and this episode we're going to try and actually make at least one arm of the real Ultron move from one of these, and if we're lucky we might get onto the head as well, and I've got another head tracker which is head mounted here, so let's get right on with it. I need to mount a number of motor drivers in the robot. I'm using the BTS7960, which is fairly high current. Each one of these will drive one motor. So altogether I need 5 of those on each side of the droid for the basically 3 axis in the shoulder, the elbow and the ab actuator. So that's 5 each side, 10 altogether. So there's going to be one mounted in the arm for the elbow and the other 4 on each side need to mount in the torso. So I've made these brackets here, which have a piece I solvent weld onto the robot, which screws onto the bracket, and each one of those is going to carry 2 of these stacked this way. Let's get that the right way round, and those will screw on there. Then the whole thing is removable, and I can take those off if I need to, and I can remove the whole thing. So I'm going to get those mounted, then we can start wiring the motors in. Here they are, all mounted up and ready to be put into the robot. I've located 4 of them down here in the torso. They should be okay, that they won't touch this actuator as the body skews. They may not be the final resting place, but of course I can unscrew them from their mounts and move them. And I fitted the final 2 actually up here. Now they were going to stick out the other way, but the shoulder hits them when it moves up. So I've put them there. I haven't put the other 2 in again. It might not be the final resting place. I was thinking in fact about stacking all of them in the back in a line on the back features actually inside a removable panel when it comes to it, but for now that'll do for testing. This is a fairly temporary arrangement, but I've got an Arduino Mega here. I've got 5-volt power distribution here, which takes 5 volts to all the motor drivers and to each end of the pots, so that I can get feedback. So my 3 pots come to the analog ins, which are just here. I've got PWMs coming out of here, and basically pins here for the enable pins on all those motor drivers. And all of those are wired in, so I've got power and motor. Motor will go in there, battery comes in there, 5 volts PWM and enable goes in the back. So there's 2 stacked up here for the 2 upper axis and 1 down below that does that 1 actuator for lifting the arm at the moment, and there will be that second one for the abs once that's sorted. So I can stress that this is completely temporary. I need to find a place to mount this properly, and there's going to be 2 of these to control the body, 1 for each side, then something else for the head and any other features. But now if you look back on the code for last time, I can re-implement my PID controllers, but 3 of those axes in one Arduino that I can then control over serial data, and then we can plug in the data from the motion capture suit. Let's just do a bit of a recap on this motion capture suit. So what I've got here is a belt which has another Arduino, and it also has a Bluetooth shield on it, so this is completely wireless. This is clipped on the outside of this belt at the moment, but it will of course be in the pocket. So I've got a battery powering it, and all the inertial measurement units are plugged in here, and those go into the Arduino there, and I've got an I2C multiplexer so I can read them all, and that data is basically transmitted over Bluetooth. Here's one of my sensors. So these are Adafruit BNO055 IMUs, which is a Bosch part on an Adafruit breakout board with an Adafruit sensor library. I've got a little power LED there just so I can see that each one of these is powered up. This is the one from the left arm, and the data that comes out of these is Euler angles, which is spelt Euler, and some extremely strange things seem to happen. And I spent quite a long time working this through in part 3 to work out what exactly was happening. So basically, for instance, the rotational axis actually stays in space. So even if I tip this up and then rotate it on its end, the data that comes out doesn't stay with the IMU, it stays with an imaginary line in space, which was incredibly confusing, but I ended up building this arm that inherently uses Euler angles, which is driven by that, and that's what I did in part 3 to work out what was going on, and I labelled the axis for each of these, and I've structured the real Ultron in the same way, so I should be able to just translate that data straight onto the real Ultron, and that should actually make it work. I've got one axis sorted, so I've got one IMU here, which is from the left arm, and if you remember from part 1, the robot is going to basically work out what to do with its right arm based on the limb positions of legs and arms and head and so on. So for now this is set up just to simply mirror, so if I move this up, we should be able to see the arm raising up there. And I can control that pretty well, so there's just a little bit of scaling that I had to do, but essentially I've just plugged the IMU data straight into that PID controller. And now I can move the arm, and of course it hits its end switch when your arm is down, so it's not constantly trying to adjust. And as you would raise your arm up, then Ultron would mirror you. But have a look at that part 1 and part 3 for further information on what the intention is here. So now I just need to get the other 2 axes working, and we should have full control. I now have all 3 axes working. I've attached a piece of foam to this so you can see where its arm would be, but that's just a placeholder so you can see where the plane is, because that's going to move around. I should add the Arduino is completely wireless. That is actually connected to the Bluetooth shield, and the cable coming out is just power that's going to a USB mains adapter on the floor. I've got a battery down there as well to power the motors. So I've put my IMU on a little tripod down here so I can hold it level for testing. But you'll notice I've got the other axis working now, so we've got the existing one, which is still quite good. I've done a little bit of tuning on that so that it's a bit more gentle. Have to forgive the foam wobbling, but obviously that's temporary till I build the forearm. And now you'll notice if I move this forwards, it uses all 3 axes. So you can see that foam rotating to try and stay parallel. There's probably some scaling to do there. Let's just twist that foam back a bit. And this is exactly the same as the test arm did in part 3. And obviously if I put this out and I twist this way, we can still twist the forearm. And it's quite reactive, so with the elbow bent on that, it'll be able to twist its forearm to put the elbow in front of it. And if I just put this forwards and backwards, you can see it using all 3 axes there to try and keep that bit of foam parallel. I think it's overcompensating when it goes back. Hard to say, but nonetheless, kind of okay with the range of motion I've got there. There is a bit of wobble in the robot torso due to the fact it's all mounted on NinjaFlex bushings and things. I do need to put some acceleration in here and some smoothing on the data that's coming out of the IMU. Obviously the motors will only turn so fast, so there's some smoothing anyway, particularly in the up and down axis. But the others are a bit jolty, so yeah, we need to do some data processing. But that'll come higher up the sensor chain along with the series elastic actuators for force feedback. But on the whole, I'm pretty happy with the motion that I've got there, and that I can drive this from this inertial measurement unit, making up the motion capture suit. Just thought we'd have a closer look at all of those axes working together as I move the sensor. So you can see these rotating together as I'm putting the sensor backwards and forwards in a plane, and that's in order to keep the arm straight. But I still have independent control over that axis. And really watching part 3 where I explain how this sensor works and what Euler angles are, it's kind of really one to watch if you're interested in knowing what on earth's going on and why the robot's structured this way. Let's see if we can do the same thing with the head mechanism now. So this is going to rotate, and it's on a gimbal, you can just about see there, that pans and tilts. So first of all, I need to put some position feedback on the motor that causes it to rotate, and I need to fix this piece on because there's nothing holding it at the moment. So that probably needs a solvent weld. And then I need to make these more flexible because at the moment it can't turn very far. There's 2 servos in the base here which are going to push and pull that. You can just about see them there, hiding behind the motor driver. So there's one on each side that will pan and tilt this about, and the rotation will come from the motor. So let's see what we need to do about that. Here's my new push rod, which is going to be made in two materials. So it's going to be printed on the TAS with dual extruders. Have a look at my unboxing video for that. Basically, I can print some in NinjaFlex and some in ABS, and print them in the same print with the two nozzles. So that'll make me a super strong bonded part, with the ends being flexible. And I've made this kind of overlap part where they're sort of stuck inside each other to get a really good bond, but NinjaFlex sticks really well, especially if the layers are built up as it melts the plastic together. Here they are. I've done two of them, of course, and they've come out pretty well. So obviously the ends are NinjaFlex, which is really flexible, and the seam line there's come out pretty clean, so those are fixed in really well, and that should make me some good rods. I've put those on, and obviously that gives me much more flexibility now, so I can make that solvent weld and get some feedback on the motor. I'm going to take position feedback from this gear, and although it's smaller than the main gear, it doesn't rotate round many times to make this do a 180, which it doesn't even need to do, so there's more than enough travel on the pot. And I've just made another one of these little brackets with a hole in to put the pot in, so it can be aligned with that, and a little stilt thing there so I can remove it if I need to. So I've got my feedback on the motor at the back, and I'm just driving that with an L298 motor driver, which should be more than enough just for that one. It's not getting too hot or anything, although it's kind of on the edge of the current probably for that quite large motor. Have a look back for the part where I implemented the neck to see what I've implemented there. But basically I've just implemented PID again for one of the IMUs. I'm using the same IMU, but eventually it'll be the one attached to the head, so all of the joints will work independently. And I've got the rotation sorted, so yeah, that seems to work pretty well. Tracks pretty well. I suppose having that good gear ratio on there really shows what you can do to build your own servo. So next I just need to sort out these actual servos to push and pull this so that it can pan and tilt as well. And we'll see if we have them so they move slightly when this twists, so that this doesn't tilt as much as it turns, but that's just going to be some coding I need to do there. The other axis are now implemented, so as well as being able to rotate it, I can also move all around. So look up in that direction. There is some constraining going on, so it won't go past its end stops on those servos. So up and down is kind of an interesting range of motion. And of course I can tilt side to side a lot better because the leverage angle is shorter on this gimbal, so let's just look over there, and I can still tilt quite a bit before I break it. Obviously, you probably need to constrain the rotation as well, but on the whole, quite a good range of motion actually, compared to a human head. Not sure, I guess I can turn about 180. Probably don't need to do that with this. I think that'll probably do for a robot like this. But yeah, I seem to get quite a lot of a good rolling motion in that with all three axes. So yeah, pretty happy with how that works out. And of course there will be separate IMUs on the motion capture suit for each aspect. So the head will of course be independent, even though I'm using the same IMU here just for testing. I'm pretty happy with how this has worked out. I had to obviously stop with the main mechanical build and do just this testing to check I could drive it from the IMUs that make up the motion capture suit. Of course all this electronics is pretty temporary, but I can now design the rest of the cosmetics and so on so that all of those motor drivers and the Arduinos and things fit in. It'd be really good to have them in panels that open up on the outside so I can get to them rather than being kind of embedded in the robots, and that's something I can really think about with the rest of the build. One other idea I did have was, instead of having motion capture, to have a little character like this with arms and things you can manipulate, maybe about twice as big, with the IMUs mounted on it. And that will give the public an opportunity to be able to control the robot through motion capture without putting the whole suit on. So this is intended to be quite a social robot that's going to go to conventions and Maker Faire and things like that. So that'd be a really good way to get an input to the robot, as well as other sensory input and other things like that. And don't forget, there is going to be an AI in between the motion capture suit and the robots. Of course, it'll only respond when it's in the right mood to do so. And the brain is also going to be quite socially interactive, so it's going to have indicator lights and things all over it, so you can see different registers for different moods. But have a look in part 1 to see what that's about. So that's all I'm going to do for this episode. I can now get on with the rest of the mechanical build. I quite like to build the head next, and obviously the arms need doing as well, which is going to be quite an interesting part of it. So don't forget to subscribe to check out more about this video and all the other projects as well, and the social media links in the description to this video.